All right, so the one thing that is interesting with this is that because of the third law, when we interact with something, the force that we exert on the other thing is exactly equal in magnitude to the force exerted back. It's also impossible to push on something longer than it pushes back on you. So if there are no external forces, if there is no extra things going on in this, the amount of momentum in a system is going to be constant. And when something in a system is constant, we say that it's conserved. So in collisions, as long as there's no net external forces, momentum is going to be conserved. And so if we look at our diagram here, we have A and B are coming towards each other with certain speed. They have a certain momentum. They collide into each other. And then afterwards, they bounce away. And we're saying that the momentum that they totally have here and there is always the same. It doesn't change. Now, the energy does change. And you'll see that in the Julia Sumner Miller video that I also assigned there, that very often we confuse momentum and energy. So more formally, this conservation of momentum says that no matter what's going on, if it's a closed system with no forces acting on it, the total amount of momentum is always going to be the same. So we have a train going to the side at 24 meters per second that is colliding with an identical train that's at rest, that's not moving at all. And then afterwards, they couple together, they stick together, and they're going to move to the side. So if this one is a mass of m and this one is a mass of m, when they stick together, they'll have a mass of 2m. Their momentum to start with would be m times 24, because this one's at rest, right? So that would be plus m times 0. So it's just going to be 24m. That's our initial. Afterwards, they have 2m, but we don't know what this final velocity is. Well, it has to be equal to the same thing it was before, which was 24m. So that means that my v prime is going to be equal to 12. So when they stick together, they're going to be going half as fast. They still have the same amount of momentum. And this is going to work for a rocket as well. So our rocket is not moving. It has no momentum. Once it starts firing gas backwards, the gas has momentum backwards. The rocket has momentum forwards. These two arrows together would be equal to 0. So it begins with 0 and it ends with 0. So this is going to hold true for collisions and for explosions. And explosions aren't as dramatic as they sound. It's just what we call it when things start together and then separate apart. So very often it would be two things with a spring in the middle, or it could be two people that are pushing away from each other. I did examples for you guys with the carts that had the push-in spring thing, and I changed the mass and increased it. We're going to have multiple types of collisions. We can have ones when objects bounce off of each other. So they could have each individual momenta to start with, and then final momenta. And you'd have to look at their mass times velocity for each case. All right, so first example. A 30-kilogram girl is ice skating at 4 meters per second. She collides with the 5-kilogram gnome at rest. I should put little zeros after those, right? After the collision, she's now traveling at 3 meters per second. And she still has 30 kilogram mass. How fast is the gnome going? So you might remember from the predictions, or if you haven't seen it yet, when a thing that's more massive collides with the thing that's less massive, it's a much bigger deal to the thing that's less massive, and that thing really jumps off. So I'm going to say that momentum is conserved. So I'm going to put a lowercase p is equal to lowercase p. I'm going to put a little 0 on the 1 for it to be an initial. And then beforehand, this girl has a momentum that's going to be m1 v1 naught. This gnome has a momentum that is 0 because anything times 0 is 0. So my initial momentum is just going to be 30 times 4. We have to have the same amount of momentum afterwards. She's going to have a momentum that is m1 times v1. So this is going to be 30 times 3. And the gnome, we know his mass, but we don't know how fast he's going. So this is going to be equal to 5 kilograms times V2. So to get V2 by itself, is there anything that I can add or subtract? Yes, I can subtract the 30 times 3. So I'm going to have 30 times 4 minus the 30 times 3. Is there anything else I can add or subtract? No. So then you ask yourself, is there anything I can multiply or divide? And I can divide both sides by 5 kilograms. So I get that V2 is going to be equal to, this is 120 minus 30 times 3, which is going to give me 120 minus 90, which is going to give me 30 kilograms meters per second, divided by 5 kilograms. And so the gnome flies off at 6 meters per second. This is what you would expect when something heavy collides with something light, that the light thing bounces off. You can also have objects stick together, so they'll have individual momenta to start with, and then a combined momentum afterwards. And so we have m1 v1 naught plus m2 v2 naught equals m1 plus m2 times v. So a 75 kilogram man is standing on a frictionless surface. He is hit in the head by a snowball. So I'm going to have a beginning and an end. I'm going to draw my man. Here's my snowball. This has a mass of 0.5 kilograms. He has a mass of 75 kilograms, but he is at rest. Put a nice winter hat on him. Afterwards, the snowball is going to be attached to part of his head. And so they have a combined mass. So now my mass is 75.5 kilograms, but we don't know how fast they're moving. The snowball initially is going at 30 meters per second. So that's a pretty fast moving snowball. But I know that these guys have to be going that way because the whole system starts with momentum that's going that way. All right, so I would write that momentum initial equals momentum final. My momentum initial is going to be 0.5 times 30. My momentum final is going to be this new 75.5 kilograms times whatever our final velocity is. He doesn't have any momentum because he's not moving. So only things that are moving have momentum. And so now my snowball and man combination, they're together. Like the picture that we saw in the notes where the two trains stuck together. That's another idea of things colliding and sticking together. And so I'm going to divide both sides by 75.5, and I get that V is equal to 1/2 times 30 would be 15. Divided by 75.5. It's going to give us like a 0.2 meters per second. So our velocity is 0.2 meters per second. And that's the combination of the two. And that would be going to the right.